Audiobook Academy Biography presents Johannes Kepler. 1. Planets orbit the Sun in elliptical orbits. 2. The time it takes to traverse any given arc of a planetary orbit is proportional to the area of the sector between the central body and that particular arc, the area, all of which were discovered by German astronomer Johannes Kepler, born December 27, 1571, in Wilderstadt, Württemberg, Germany, died November 15, 1630, in Regensburg. When Isaac Newton deduced these discoveries from a new and different set of universal physical principles, he called them laws. Kepler himself did not name his discoveries laws. He saw them as divinely inspired melodies, a reflection of God's original vision for the cosmos. Nicholas Copernicus's sun-centered system was transformed into a dynamic world by Kepler's discoveries. The Sun was actively pushing the planets about in non-circular orbits. For other key 17th-century world system designers, the most famous of which was Newton, Kepler's concept of a physical astronomy fixed a new dilemma. As part of a long list of accomplishments, Kepler provided an accurate theory on the origins and function of vision, developed an entirely new theory on how the telescope's light behaved and found new, semi-regular polyhedrons, and he also developed an entirely novel theory on astrology while also restricting its predictions to a specific area of the sky. An enumeration of his accomplishments, on the other hand, fails to show how important they were to Kepler as a contributor to a larger body of knowledge. Kepler's scientific achievements evolved from an uncommon and fascinating mesh of theological, astrological, and physical beliefs. But because of the originality of Kepler's discoveries, it is necessary for moderns to comprehend how such lasting outcomes could have come about from such an odd combination of concepts. According to current understanding, astronomy, the study of celestial bodies' motions, is part of a larger field of inquiry called the science, which encompassed many different disciplines. Mathematical and physical components were seen as integral to the study of the stars, which was viewed as similar to music, the study of ratios of tones, and optics, the study of light. It was further divided into theoretical and practical sections. Beyond the theory of celestial motions, there was the practical construction of planetary tables and instruments. Similarly, astrology's theoretical principles had an accompanying practical component that dealt with the production of annual astrological forecasts about people or cities or the human body or weather. As a result, Kepler not only successfully integrated astronomy into natural philosophy, but he also made groundbreaking advances to astronomy and its ancillary fields. Social world. In the latter half of the 16th century, there was no such thing as a scientific community. Whether Roman Catholic or Protestant, the educational systems in Germany, as in other countries, were all controlled by religious institutions, and local rulers exploited them to strengthen the loyalty of their populace. One way to achieve this goal was to establish a scholarship program for underprivileged boys who, after attending the duchy schools, would have a strong sense of allegiance to the ruler of the region. Kepler was born in Wilderstadt, a tiny German town, and received a ducal grant to attend the Lutheran Stift, or seminary, at the Academic of Tübingen, where he began his university studies in 1589. Teachers, ministers and other government officials were required to be graduates of these schools. At one point in his life, Kepler considered pursuing a career as a theologian. Not everything went according to plan in his personal life. Divine providence led him to the study of the stars, he said, and he never lost sight of the fact that his true calling was one of service to God. When Copernicus made his offerings at the high altar, he wrote, "I am satisfied, to guard the gates of the temple." Michael Maestlin, one of Germany's greatest astronomers, was the mathematics professor at Tübingen, where he taught from 1550 to 1631. One of the few Copernican believers in the late 16th century, Maestlin was a Lutheran pastor, but he was careful about expressing his ideas in literature. He gave Kepler a copy of Copernicus's De Revolutionibus Orbium Coelestium Libri, 6 books on the revolutions of the heavenly orbs, which was significantly annotated by Maestlin. Maestlin taught Kepler the complexities of Copernicus's work, which he rapidly mastered. Copernicus' description of the world contained the mark of divine planning, literally a revelation, and he recognized it immediately. While still a student in the early 1590s, Kepler set out to prove what Copernicus had only speculated about. Even though it was done through the use of religious and philosophical language. It wasn't just Kepler who thought that nature was a book in which the divine purpose was inscribed. He differed, however, in the originality and emotional intensity with which he held that his views were incarnate in nature. To him, a geometric sphere, representing the Christian Trinity and hence the visible, created universe, was a literal reflection of the divine mystery, God the Father, center, Christ the Son, circumference, Holy Spirit, intervening space. "And the Word became human and dwelt among us" was one of Kepler's favorite Bible verses. A geometric representation of the divine archetypes, straight and curved, was interpreted by him to mean that the spatial arrangement of actual, corporeal creatures was arranged according to these geometric forms, which were clearly visible. Another aspect of God as depicted by Kepler is an ever-evolving creative power, symbolized by the Sun's body as the source of dynamic force that perpetually shifts planets in their orbits. There was a perfect mirror in the natural world to show off these divine concepts. According to Kepler, who was inspired by Platonic concepts of innate thoughts in the soul, the human mind was designed to comprehend the world's structure. Johannes Kepler's astronomical contributions. Kepler's first work Mysterium Cosmographicum, 1596, Cosmographic Mystery, contained many of the concepts that he would explore for the rest of his life. Professor of mathematics at the Protestant seminary in Graz, Austria, in 1594, Kepler was also the district mathematician and calendar maker for the area. When Kepler was teaching a class in 1595, he had an epiphany. One of the regular polyhedrons could be used to circumscribe and inscribe each orbit of the 6 Copernican planets, he realized. A perfect concept, according to Kepler, must have been implied by Euclid's proof that only 5 such mathematical objects can be composed of congruent faces. As long as the ratios of the mean orbital distances match the ratios determined by circumscribing and inscribing the polyhedrons, Kepler was convinced that he had uncovered the universe's architecture. With the exception of Jupiter, Kepler found agreement within 5%, which he remarked no one will marvel, considering such a huge distance, was remarkable. "I wanted to become a theologian, for a long time I was restless," he wrote to Maestlin. "God is being honored in astronomy as a result of my efforts." However, Kepler's study on planetary motion would not have deviated from the ancient Greek concept of uniform circular planetary motion if his investigation had ended with the discovery of this architectonic principle. The God of Kepler, on the other hand, was both ordered and active. While Copernicus's passive, resting sun had long been held in high regard, Kepler proposed that a single force from the Sun is responsible for the planet's ever longer periods of motion as their distance increases. Although Kepler did not yet have a precise mathematical definition of this relationship, he intuited that there was some sort of link. Following his acquisition of William Gilbert's De Magnete, Magneticis Corpore Orbis, and De Magno Magnete Dolor, 1600, he quickly adopted Gilbert's thesis that Earth is a magnet. This was a few years before his death. When Kepler looked at the magnetic bodies in our solar system, he concluded that the Sun's rotation sweeps them around, with their matching like poles repelling and their opposite poles attracting. Mars' orbital theory relied on Kepler's understanding of the solar force, which decreased in inverse proportion to distance in the orbital planes. But there was more. Kepler held himself to an exceptional standard of empirical precision for his period. Tycho Brahe, the famous Danish astronomer who lived from 1546 to 1601, had set himself the goal of reforming the foundations of practical astronomy by collecting a fresh set of planetary observations. Tycho invited Kepler to his court in 1600 at Castle Benátky near Prague, where Kepler accepted. When Holy Roman Emperor Rudolf II's imperial mathematician Tycho Brahe died unexpectedly in 1601, Kepler stepped in to fill the void. Imperial mathematician Kepler's initial work was a break with Ptolemaic astrology's theoretical assumptions. New physical and harmonic principles were offered to make astrology more definite in a treatise titled De Fundamentis Astrologiae Certioribus, 1601. Concerning the more certain fundamentals of astrology. Kepler's intellectual independence in rejecting much of what was supposed to be known about stellar influence was shown by this. Kepler's unexpected inheritance of Tycho's observations bolstered the intellectual independence that Rudolf's court had previously enjoyed. Tycho was very private with his observations during his lifetime. Kepler was able to work with data that was accurate to within 2 of an arc after Tycho's death, despite a political battle with his heirs. As a result, Kepler couldn't have discovered his first law, 1605, which states that Mars travels in an elliptical orbit around the Sun. A 6 or 8 foot mistake developed in the octants at one point, for example, when he sought to balance the necessity for exact heliocentric distances with a circular orbit, assuming a circle divided into 8 equal parts. It was Kepler's declaration, because these 8 could not be disregarded, they alone have resulted in a complete reformation of astronomy. With Kepler's reshaping of astronomy and Tycho's rethinking of astrology's foundations, astronomy has never looked better. A similar relationship existed between planet spacing and polyhedral shapes, and Kepler only considered the rays that impacted Earth at harmonic angles that were compatible with his theory of planetary motion to be of use. After winning his war on Mars in 1601–05, Kepler wrote major treatises on the nature of light and the startling emergence of a new star, 1606, on the new star, during this creative explosion in Prague. In October 1604, Kepler first observed the star, which is now known to have been a supernova, after a conjunction of Jupiter and Saturn in 1603. Even though this particular conjunction occurs only once every 20 years, it gained even more astrological significance when a supernova appeared out of nowhere. As was customary for Kepler, he used the occasion to make both practical predictions, such as the fall of Islam and the second coming of Christ, and theoretical speculations about the universe, such as the idea that stars are not the result of random atomic combinations and that they are not the sun. As an astronomer, Kepler was interested in how light rays from distant celestial bodies are deflected as they enter the Earth's dense atmosphere, and subsequently, how light rays are deflected as they enter the denser medium of the eye. However, as always, Kepler approached these issues from a unique perspective. Kepler, despite his position as a court astronomer, opted to present his theories on light in a more typical academic format. Ad Vitalionem Paralipomena, Quibus Astronomiae Pars Optica Traditor, 1604, supplement to Whitlow, in which the optical part of astronomy is explanated. The most important medieval treatise on optics was produced by Whitlow, Latin, Vitellio. However, Kepler's study of vision altered the conceptual foundation for analyzing the behavior of light. Every point on a luminary in our field of vision emits light in all directions, but only those rays that impinge on the pupil, which acts as a diaphragm, can reach our eyes, according to Kepler's theory. His visual cone was likewise inverted, which was a first in his field of study. It was claimed by Kepler that the light rays from one source form a cone, and the base of the cone is located in the pupil. It is only after this that all the rays meet again on the retina that they can be seen clearly. Pencils of light composing upside-down images were for the first time considered to be composed on the retina, the sensitive receptor of the eye. A faulty eye causes fuzzy vision because the second short internal cone reaches to a location that is not directly on the retina but rather in front of or behind it. People have relied on eyeglasses to improve their vision for almost 3 centuries. But no one before Kepler had a decent explanation for how these little curved pieces of glass had been able to function. Sidereus Nuncius, 1610, the sidereal messenger, recounts Galileo's discoveries after he had built a telescope in 1609 and had revealed previously undiscovered celestial objects, such as moons orbiting Jupiter, and flaws in the lunar surface. In response, Kepler published 3 major treatises. His Dissertatio cum Nuncio Sidereo, 1610, Conversation with the Sidereal Messenger, in which he postulated that the distances of the newly found Jovian moons would accord with the ratios of the rhombic dodecahedron, triicontohedron, and cube. To learn more about telescope optics, the second book was titled Dioptris, 1611, Dioptrics, which included a detailed explanation of a new design that utilized 2 convex lenses. Narratio de Jovis Satellitibus, 1611, narration concerning the Jovian satellites, was based on his own observations of Jupiter taken between August 30 and September 9, 1610, and was published in 1611. I thank you because you were the first one and practically the only one who had entire faith in my declarations, Galileo wrote to Kepler, who had never been particularly nice to him. During the year 1611, Kepler's life took an unexpected turn for the worst. In addition to his wife Barbara falling ill, one of his sons died from smallpox, as did his other 2 children. Rudolf was soon forced to step down as emperor. As far as Tübingen's theology faculty was concerned, it was Kepler's ironic theological ideas and affiliations with Calvinists as well as Catholics that did not help him in his quest for a new academic position. Meanwhile, at Linz, Kepler was assigned to the district mathematician position, which had been specifically created for him. Even though he was physically expelled from the Prague court by the new emperor, Matthias, he retained his post as imperial mathematician. After his wife died and he was excommunicated from the Lutheran Communion, Kepler continued to produce works of art in Linz until his death in 1626. 5 of his 7 children from a second marriage in 1613, to Susanna Riedinger, died as infants. During the Counter-Reformation, Catholic authorities temporarily seized his library and required the children to attend church. In 1615, Kepler penned a theoretical dissertation on wine barrel volumes in response to a real-world challenge. He released the first book in Linz, Stereometria Doliorum Vinariorum, the stereometry of wine barrels. Wine merchants' rule of thumb methods for estimating a barrel's liquid volume rankled with Kepler. It wasn't enough for him to simply follow Archimedean methods, He went on to add solids generated by rotation about lines in the plane of the cone other than the principal axis to the conic section's range of possibilities, thus expanding the range of cases in which surfaces are generated by a conic section. It was expected that Kepler would devote the most of his time to completing the astronomical tables that Tycho started. Kepler, however, found the labor dull and resumed his search for the world harmonies that had fascinated him since his childhood. With his Harmonice Mundi, Harmony of the World, Kepler compiled more than 2 decades of research into the world's archetypal principles, geometric, musical, philosophical, astrological/astronomical/soul-related principles. Kepler's third law was included in this compilation. Polygons were divided into equal parts in order to establish just ratios: half, 2/3, 3/4, 4/5, 5/6 and 3/5, rather than the Pythagorean scale's irrational ratios. An ethereal influence was felt when the planet arranged itself in uniform polygons. This arrangement was made possible by the planet's extreme velocity ratios conforming to the harmony of the just tuning system, which was a celestial melody that did not sound. Copernican Astronomy Textbook Epitome Astronomiae Copernicani, 1618-21 was produced by Kepler in 1618-21. When it came to content, the title could not have been more dissimilar to Maestlin's standard textbook. Starting with the basics of astronomy and adding in all the evidence for Copernicus's theory, the Epitome compiled all the evidence and added in new principles of planetary motion to support it. The Copernicans would turn to this text as their primary theoretical resource in the 17th century. Perhaps Galileo and Descartes were inspired by it. Tabulae Rudolphini, 1627, Rudolphini tables, was the final straw. Using the Rudolphini tables and the Epitome, heliocentric astronomy and astrology were given a form that made it difficult for anyone who disagreed with them to avoid engaging in counter-argument. By this point, Newton would have taken over all of Kepler's rules without regard to their religious or philosophic contexts. 10 years after his death from cancer, Kepler was in constant pain. His mother was accused of witchcraft in 1615 and fought her accusers until 1621, when she was finally exonerated. She died a few months later. This assistance for his mother required a great deal of travel, court briefs, and other tactics that badly hampered his employment. Albrecht von Wallenstein, an imperial general, became Kepler's new patron in 1627. Wallenstein arranged for a printing machine to be built for Kepler in Sagan, Silesia. After receiving Wallenstein's request, Kepler properly prophesied terrible disorders for March 1634, which was the date of Wallenstein's murder. When Kepler tried to collect money owed to him, he had less luck. A month after Wallenstein was ousted from command, Kepler departed for Regensburg in an attempt to collect interest on some Austrian bonds owed to him. It wasn't long after arriving at the hospital that the patient became extremely ill and died on November 15. The 30 Years' War swept away his grave, but the inscription he wrote for himself was preserved. I used to measure the heavens. Now I shall measure the shadows of the earth. Although my soul was from heaven, the shadow of my body lies here. Thank you for listening in Audiobook Academy. Don't forget to subscribe and smash that like button for more content like this. See you in next video.